Hello there, thank you for joining me again today. On the bench for review is a Aeroflex spectrum analyzer. This particular model is the 3251, as highlighted here, 3251. This spectrum analyzer fully featured, quite modern spectrum analyzer in comparison to some of the other equipment that I demo on this channel, and it's in a very nice stylish case. As we'll review. It has the track gen option as well, and it features on this particular model a frequency range of 1 kHz to 3 GHz, which is quite a wide frequency range, especially starting at 1 kHz. It's a very advanced, very fully featured test instrument. It's a little different to some of the other spectrum analyzers that reviewed before on the channel, and it's got rather a nice like holographic spectrum analyzer logo on the side. It's a plastic case, quite heavy. I must admit it's probably not far off the weight of a Marconi radio test set to 2955. It's very heavy, but yeah, as you can see, it's quite nice. It's got little feet underneath that can bend back and forwards, so you can obviously have it propped up like this or stack it on top of other equipment. This particular machine is quite nice with the graphical user interface, with it being a colour display, a touch screen as well. You can touch the measurements on the screen as well as pressing the shortcut buttons that appear at the side of the screen, the menu buttons. And it's got two nice big carry handles on the front here, quite chunky beast things to obviously carry it from site to site. Been well thought out really with its design. USB ports at the front, and quite a lot of features on it, as you can see. Now if we turn it round just for a moment, have a look at the rear. We've got these nice chunky rubber boots that prevent any damage from when it's laid on surfaces, etc. And then on the rear we have obviously the software license here. I think it runs Windows XP, and we have also some BNCs for optional signal inputs and outputs, for sweep generators, for driving different external equipment, frequency standard inputs as well, different options that are fitted on it. And then we also have a serial port, a VGA port on the output as well, an Ethernet port, and then two USBs, the various fans on the power supply, etc. And then underneath here we've got the GPIB socket, an earth terminal, and just a fan and IEC, and that's about it really. On the rear, quite well protected with these plastic corners, so if you do sit it on its back without the mains lead plugged in, it won't damage anything. So they've thought about how you're going to move it around and do whatever. So that's a little rundown of the rear of the unit. Not much really on the back, but yeah, this spectrum analyzer is quite full of features. I'll go into all the features and we'll do some measurements with the track gen as well as just with a signal input and its capability. But just to read a little bit about what it says in the product manual, it says here the instrument is a portable spectrum analyzer. It's suited for signal analysis of high frequency digital radio equipment. It says the instrument uses a synthesized local oscillator to cover the following frequencies. So this model is the first model in the range, 3251, and this covers 1 kHz to 3 GHz. The next model up is the 3252, is 1 kHz to 13.2 GHz. 1 kHz to 8 GHz. And the model up from that is the 3253, which is 1 kHz to 13.2 GHz. And then the 3254 model, the top of the range one, is 1 kHz to 26.5 GHz. And it says here, it says a spectrum analyzer provides excellent distortion and frequency and level accuracy performance and easy operation using the soft key menu screens. And it says here it provides excellent cost performance with a choice of options for various applications. It's equipped with highly accurate calibration signals and attenuator so that it can accurately calibrate switching errors on log and linear scales, various resolution bandwidths, variable reference levels, etc. As frequency response data is corrected by built-in calibration data, the instrument provides accurate level measurement over a wide range. It says the measure function performs measurements of various applications without requiring the use of an external controller. In this way, the performance of radio equipment can be easily evaluated in terms of frequency, noise, occupied frequency bandwidth, and other important parameters. It says that the applications for this spectrum analyzer, it's designed for use in production and maintenance of the following: AM and FM radio equipment, digital cellular telephones and cordless telephones, satellite broadcasting and TV equipment, and small capacity microwave equipment, wireless LAN equipment, etc. Now, it does say that there are various options, so we'll have a look at that a bit later in the video as well. But basically, the frequency reference has got a temperature drift specification of 1 parts per million, plus or minus 1 parts per million, plus or minus 0.1 parts per million on an option. Frequency readout is 1 Hz minimum. Resolution is available in 1 Hz, 10 Hz, 100 Hz and 1 kHz. And the accuracy of the frequency accuracy, the X marker and counter resolution is plus or minus 1 LSB, least significant bit. And the sensitivity is minus 45 dBm at 13.2 GHz for frequencies 2 MHz span to 3 GHz, and minus 40 dBm at 26.5 GHz for frequencies at 13.2 GHz with a span of 3 GHz. It says the frequency span or 0 Hz span is available on all the 3 different frequency ranges with a resolution of 1 Hz and accuracy of plus or minus 1%. And also for the sweep generator, it says it's 1 microsecond to 2000 seconds plus or minus 0.5%. And the span at 10 Hz resolution is 10 milliseconds to 2000 seconds plus or minus 0.5% nominal. And the sweep points are 3 to 8192 for a span of 0 Hz, and 101 to 8192 for a span greater than 10 Hz. Talks about spectral purity at 1 kHz offset is neg 92 dBm, or typically neg 95 at 1 GHz, and then it gives some information about resolutions as well, different filters, and rattles on about quite a lot of other spec which I'll not go into at this stage. But basically it's a very nice spectrum analyzer, quite well featured, and the different options I can see there. Option 1 is a 3 GHz tracking generator. Option 3 is high stability oscillator. Option 5 is an external pre-selector AB band. Option 6 is AC/DC power supply. Option 8 is a GSM edge measurement suite. Option 9 is UMTS UL measurement suite. Option 10 is a CDMA measurement suite. Option 11 is a wireless LAN measurement suite. 12 is a WiMAX measurement suite, and 13 is an EMI, electromagnetic interference measurement suite, and option 14 is an LTE measurement suite. So there's quite a few little options on it, you know, that you can get. Very nice little unit. Now, to have a look at the spectrum analyzer, it's the same old story really with them all. You know, we've got the usual frequency, span, amplitude, then we've got the markers as well, which we've got here on the red keys. and all the different capabilities that it can go into. This one's got some more features on it which you don't see on some of the spectrum analyzers from Hewlett Packard, the older ones that I've demonstrated as well, which I'm going to show you. So anyway, we've got a signal generator on down here at 1 GHz, giving a 0 dBm output. So we'll just connect that up, and we'll do some measurements and show you what it can do. So if we type in the frequency, we've got an option here for center frequency and obviously start and stop frequency as well if we want to put that in. So I'll just go for the center frequency of 1 GHz. Now you can either press the key or touch the screen, and then obviously we can go to the level as well, amplitude, so we can either turn the rotary control or use the up and down keys here. So obviously I'll just bring that signal back just below the top line, and then what we can do is we can obviously use the markers if we wish as well. So we've got a delta marker if we want to use that. So obviously if I reduce the output signal from the signal generator, it will tell us what the difference is on the screen. So I'll just do that. If we can select RF level on there, and then put in, say, -10 dBm, and so it's 0 dBm again. Zero dBm, and then -10 dBm. So then it's telling us what the difference is, -20 dBm. So that's obviously, you know, showing us on the screen there what we've got here, -20 dBm, and then it's showing us the difference, which is obviously at what it's showing us. Gives us quite a bit of information around the outside of the screen edge here as well. So it's quite a lot of data available on the screen on this one, whereas other spectrum analyzers that I've seen that are in this sort of age bracket, they tend to just concentrate on the trace, and the rest of the data is accessed through menus, whereas this test set, it does tend to put quite a bit of information around the screen for you, so it makes it quite easier to know what you're doing before, and you're not hopping around from menu to menu to menu. So obviously we've got a select marker, normal, delta, we've got a band pass, or what does that say, band pair, a span pair, off, marker trace A, B and C, so we can put different traces on. And obviously there's more where we can go to readout for frequency, and then obviously it will display that frequency readout. We've got averaging, marker averaging, all sorts of different parameters that we can go into. So anyway, on the normal mark, of course, by selecting that, then you can obviously read the dBm level that's coming in, as you can see there. It tells you there -21.3 dBm, which will equate for the cable losses, bearing in mind that's set to, you know, -20 dBm. So also you can do some other measurements as well under measure. On here we have channel power, so then it will tell us what the level is, and the spectral density. It'll give us all the information about occupied bandwidth as well, so we can switch that measurement off. We've got occupied bandwidth, it'll give us information on that. Measurement off. We've got intermodulation as well, so any information about intermodulation or whatever will be displayed there. and then we've got total power, and there's also I think I've done channel power, yeah, already I've done that. Occupied bandwidth, right, let's have a look. CCDFF, RDF, CCDF measure, I'm not sure what that is, but certainly working there anyway. I'll have to read about that and find out what that is. And harmonic distortion, and what that would be, so it's just waiting for the measurement to be made. We'll see what harmonic distortion that comes out with once it's done its measurements. And there we are. So it's giving harmonic distortion measurements. Measurement off. So we've got quite a bit there. Adjacent channel power as well. And it'll tell us there what any of the adjacent channel power would be. Particularly useful that for spread spectrum modulation. And I think under amplitude we've got quite a bit. So we've got different bits of functionality here. We've got the reference level we can set up. The attenuation, so we can add attenuation as well. We've got a scale division, 1 dB or 10 dB per division. Scale type, logarithmic or linear. So we can switch between that. There's an internal amplifier as well, which is quite useful for measuring very low signal levels. When that's enabled, then if you remember, if you've not seen the video that I did a while back on the 2955B radio test set repair by Marconi, in that video I demonstrated how we measured the signal generator performance of a radio test set and how we would use amplifiers externally to pull out a signal from what is the noise floor, because obviously the dynamic range of the spectrum analyzer is only suitable to about -100 dBm from the top of the scale to the noise floor, whereas a signal generator in, say for example, a radio test set can go down as low as -135 dBm. We had to amplify the signal by 35-40 dBs in order to see what the signal is at below what -100 dBm on a spectrum analyzer. And so this has built into it an internal amplifier, so that you can obviously amplify that signal and what would be pull out the noise floor. So that's quite a very useful feature, that. Then we've got reference offset as well, units, so we can measure different units in dBm, dB microvolts, so on and so forth. We've also got more options there, watts as well. We can do all sorts of things if we're using external attenuators, because again, although this instrument can only take a certain level of RF power, which is obviously denoted here, like it'll tell us on the front. If we zoom in, it'll say 1 kilohertz to 3 gigahertz. It can take a DC bias of plus or minus 50 volts DC, which is quite useful, and a plus 30 dBm maximum. So anything higher than plus 30 dBms, you'll burn the input out. So if you wanted it to be used with high-powered signals, and then to be able to tell you what the RF power is by directly measuring it, then you would use attenuators on the input to attenuate the RF signal. So we would start off with a big RF power attenuator, and as an example, if I've got one here to show you, you will perhaps use something like that, which is quite a large power handling capacity. And if this didn't provide enough attenuation in itself, then you would follow on the end of that another attenuator that has a lower power capacity, because what's coming out of here is lower power but yet still too high perhaps for the test set to measure. And then you would then have a number of attenuators depending on what you have in your stocks. I mean, some people will have different attenuators like this at different levels. Others, like myself, might just have a one attenuator, but then we'll add other smaller ones on the back of it to attenuate even further. Depends what you have available, but the basics here is that you can do direct RF power measurements from quite high powered transmitters without damaging the instrument by using RF power attenuators like this, and then you enter the offset of that RF attenuator into the spectrum analyzer, so that it can read watts directly, or RF power in watts, on the screen, and show you what the true level is coming through the attenuator. And so that's a way of direct RF measurement, where you're making power measurements and signal level measurements directly from a transmitter, be it high powered or low powered. But you need to use external attenuation, of course, for high powered systems. However, you can also do it indirectly by sniffing. As you'll see in my other videos on directional couplers, we can use a directional coupler to sniff a proportion of a signal at 20 dBs lower than the fundamental power, and then we can then read that on the test set on the spectrum analyzer. So that's a very useful feature, to have that capability where you can do either or. Obviously the direct method, then you can obviously pull out more detailed information of harmonics and intermodulation distortion, whereas the indirect method, which is sniffing a proportion of the signal by not a direct method but an indirect method of coupling a sample of the signal off, then you don't get that accuracy with some of the harmonic distortion or the second, third, fourth, fifth harmonics, etc. They can tail off quite quickly depending on the dynamic range of the sniffer that you're using, and so often it's a bit of head scratching for some people to work out how to do that directly, which is via the RF attenuator method. And then you measuring a signal directly rather than indirectly. So there are two different ways of measuring our signals, really, directly or indirectly. So that's a little rundown on that side of things. But yeah, quite a nice display. Obviously you can select all kinds of different measurement units, etc. And then on the measurement, these are the main measurements that you can do with it. Let's have a look. Is this 1x dB down? Left, right bandwidth, cross bandwidth, center frequency of bandwidth. So there's all kinds of bits of data there that you can do, and in the manual it'll explain what they are, and I'll go into that a bit later. And we've also got the peak find under the markers as well, so we can find the peak, which is done. There's marker functions, so then we've got marker noise, for example, a frequency counter, so we can, for example, put the frequency counter on, and then it will show us what the frequency is for frequency calibration purposes when we're calibrating a transmitter or a signal generator. And then we've got marker noise as well, gives us what the noise is on the marker point, and we may have to just decrease the span to say 100, and then kilohertz, and oh dear, span 100 kilohertz. If I put that right, kilohertz, there we go. Full span. Right, go to marker, or peak, find the peak, peak to center frequency, next peak look, search, signal track continuous, market center frequency. So when I press that, it should bob it to the center frequency, then span, and then if we say 100 and then kilohertz. And then let's have a look here. Let's do last span again. Just need to find out why it's right. Span 1 megahertz. Don't know why it's doing that. Let's have a look, see if we can do some diagnosis as to why. Span width 1 megahertz. Span, about 10 megahertz then. Seems a bit strange. I would have thought, zoom out, is it zoom out? No, that's why. It was fully zoomed in, that's why. Must have been whatever mode it was on prior. Okay then, so we can go to peak, and then we can do peak to center, market to center frequency. And then under measure, we've got channel power. Oh, it was under markers, wasn't it? Markers, and then I think there was under here was a marker noise somewhere. Can't remember where it was. Select marker, band pair, off marker trace. Marker, couple, sweep, bandwidth, function. Oh, there it was, marker noise, that was it. And then that'll tell us what the noise is. Marker noise. So that's how we can do noise measurements at that frequency. So that's something else that it can do. Measure off. Control, not sure what that is. Frequency counter, measure off. Sweep, what's the sweep function? So this is the tracking generator, the sweep. So we've got continuous single and the sweep of a trace as well. And I think, mistaken, there's bandwidth measurements as well. Video resolution bandwidth, span resolution bandwidth, resolution bandwidth, auto, manual, all auto. So you've got your video bandwidth and your span resolution bandwidths as well. So there's quite a bit really. Source, display, limit, trace. Press trace. Clear and white, max all, min all, view, blank, about more, sweep, average, max old, min old, view. Blank. And then if you can't get back for whatever reason, like somehow I've managed to lose myself and sort of can't get really back to where we were before, unless it's under view. There we go. You can press the preset button here, and then the preset button, then you can go to your last state and that kind of thing as well. We've also got a Windows button, so we can get to Microsoft Windows as well, and we can drive it obviously with the mouse and keyboard into the USB. We've got file, which I think is what you get to work through one of the buttons. Save, print, preset, there's tune, so it'll obviously try and find the most prevalent signal on the input. There's a trigger as well, and then we've got single, so single sweep or continuous sweep as well. So I'll find out now how we do the tracking generator measurements as well, and then I'll come back to you with that. Okay, so we're ready to do measurements now using the tracking generator. I just had to have a quick read of the manual to find out how you get to it, because quite a lot of people, a bit of a schoolboy error really, is that when you go to frequency, there is a mode there called signal track, and that isn't the tracking generator, so you've got to be aware of that. But basically it's accessed through pressing source, and then you get this extra feature then which is called TG, which stands for tracking generator, which is this TG out thing here. So you can select that or touch the screen, and then you can select tracking generator on, and then it will give a waveform. Now to normalise it, to make it normal, you just press the normal button and then it straightens it out. Now you've got an output level as well, which you can set then to say 0 dBm. So then you can select that 0 dBm, and that way then that's on the top line. I'll just normalise it again. So basically right at the top line, you can then do the amplitude to reduce it if you want, you know, 10 dB, 20 dBs, etc. You can do that, but normally have it riding on the top line, or just below it. It's up to you how you do it, but as soon as you know that the level, when we go to amplitude and then the marker, then it will read the level there anyway, which is saying is -1 dB, which is obviously at that particular frequency at 1.5 gigahertz. This lead has a 1.5 dB loss in it according to that. So if we go back to source, tracking generator, select normal to on. Oh, there we are, normalised 0 dB. So we've normalised it with that cabling. Now what we'll do, because this is obviously, if I go back to marker, if I move a marker, we can see the frequency here. That's at 1 gigahertz. So this is a full span, if you like, of the instrument that it's currently on at the moment. So to adjust that, we can go to frequency. I'm assuming we can go to a start frequency of, say, for example, 100 megahertz, and then a stop frequency. We could perhaps have that, say, at 300 megahertz, for example, and then therefore when I select marker again, the frequency, yes, it's followed it. So it starts at the far left at 100 megahertz, and then obviously as I wind the control round, it should go up to 300 megahertz. That's how I can narrow the tracking generator bandwidth. And so for example, we'll do a filter as well, but I just thought it'd be interesting to see what the attenuation specification is on this. This does say somewhere on it what it is, unless we're being tricked, unless it doesn't tell us on this. Oh, here we are, look. So it can take 150 watts maximum in the input. It doesn't. How many dBs does it say? 6 dBs. The smallest writing humanly imaginable. I've printed it on at 6 dBs. But it doesn't tell us what frequency range it's suitable at working at, does it? So we can find that out to see if it's suitable of attenuating at 6 dBs across its frequency range. So that would be the RF input, and this there is the output. So what we need to do is to connect this cable, the tracking gen output, because that's where the signal source is coming out of, into the input on here, and that way then basically we can inject a signal in there. Just make sure the SMAs are nice and tight finger tight. And then somewhere I've got a back-to-back adapter, because as usual that's what we need in this case. We need a back-to-back RF adapter, because the gender on the on this is a male. Now I don't want to attach it directly to there because this is very heavy. This is over 1 kilogram in weight, and it will put excessive strain on that RF socket there. So I don't want to damage that. So I'm just looking in my box of tricks to see whether we've got a barrel adapter, which I'm damn sure I have somewhere, but just finding it. I've got that many RF plugs, etc., that it's very difficult to find it. So I do have a barrel adapter somewhere, but anyway, I found something that might be suitable at the moment, although it's not exactly desirable, but it'll just show the point. So I've got this thing. Right, so we'll screw this on, this adapter, and right, so I'm just gonna make sure that's nice and tight, because it's just feeling a bit loose at the moment. Right, so I've got that now ready to connect up to the radio test set. And I think for that I'll probably need the other lead, which I've got, a little short lead. Again, if you're introducing all these leads, etc., when you're doing a calibration, best thing to do is to attach them all together in one continuous chain, then do your calibration, so it's taking into the factor of the measurement, the whole system, the cables, which is really what you should be doing. But I just want to show an example of doing the measurement here and not go too far in depth into the calibration routine as such. So we've got that then connected to the test set. This is going to plug in here, on there, and then allegedly, if we can get it to go on, we should have a 6 dB loss on the trace. So let's just have a look. Let's see if we can get this alternate on. Right. Interesting. Okay, let's have a look, see what we've got amplitude wise. Minus 54 dBm. I think something's wrong somewhere. Let me just check what's wrong. I was faffing about there trying to get this connection to work properly, and figuring out that the little back-to-back adapter thing I'll be using might have a fault. And it turns out, when I tried a different adapter, the whole N-type thing's unscrewing from the attenuator itself. That's the reason why, you know, when I adjusted the sensitivity of the analyzer, I couldn't pick anything up because this damn thing had come unscrewed. So may as well have a look inside then, find out what's inside. So that's the surface contact, obviously, that makes contact, I think. Let's have a look. Yeah, it's just like a little pin thing that goes into it, and then on the inside in there we go. Oh, it makes contact with the edge of the PCB with the look of it, so it's got to touch that little gold contact there. So if it's not fully screwed in tight enough, then it won't make contact with that little gold strip. So that'll be the reason why then. It seems a bit strange that. If it could be soldered, really, wouldn't you? But Obviously not. So it relies heavily then on the centre pin of that to bite into that copper, got that gold contact then, as that's screwed in. So that explains why, you know, it kept turning round, which I thought was strange. So again, you know, this is the thing with RF stuff. You know, you screw things on, and sometimes when you're a bit too boisterous with screwing the connectors on, you can unscrew things. Normally I would have expected some thread locker to have been put on there when it was manufactured, some Loctite nut lock or something like that to prevent it from unscrewing. So obviously these RF connectors will be a bit tight, and let's have a look, see if we can screw it back in and then tighten it up. Let's have a look. So it's only so tight you can go. Might have to get some pliers on it or something just to screw that in, because it's normally there's like a little flat on both sides of the end socket, which will allow you then to nip that up against the PCB internally, but that's not there. So we'll back to the drawing board now. I'm just going to refit that connector on, which we had earlier, because we weren't getting the right level, and I thought it was this, you know, this adapter, but it may still be, you never know, but it's very, very odd. So let's see if we can make it work. Now it does seem a little bit cross-threaded a little bit when it's going on. Here we are. That's weird. Don't seem to fit right. There's something not right about that. Don't seem to fit correctly. There's something weird. Some more junk that I've got. So we'll have to fit the proper McCoy, the real McCoy. These radial, high quality RF adapters. Probably throw that in the bin if the threads have gone on it. So that's gone in nicely. I've just got to find the adapter thing now to connect that to the RF cable. Probably a female version, SMA to a N-type female. So that's the next little project. I've got to find that now, so backing them out. Well, I think this is going to turn into an attenuator repair video now, because this is dicky, to say the least. We've gone to the high quality radial adapters, to SMA, back to radial adapter N-type again. So we've gone from N female to N female. But I've noticed as I watch that trace on there, if you just put a bit of pressure on there like that, you can see as I'm putting a bit of pressure on with my thumb and I'm moving it, it should be 6 dB loss, but it's all over the place. It's not these are okay, it's this N-type. So as I put pressure on there, it's going up and down. So that's obviously a fault, and so I think we're going to have to strip this down and do some repairs. And obviously it's not making proper contact with that thing, so there's obviously something wrong with it. For me to put pressure on the socket, and that happened. There might be some breakages inside or something. Seems a bit strange to me, this, so we'll strip that down now and have a look at that. Okay, well, I've tried taking this apart completely, but I can't get the last bolt out down there. There's a rounded off Allen bolt in there. All the others have come out by that one. Looks like somebody else had a go at it before me as well. So that's the RF attenuator. You can see more or less straight through, right in the middle, and it's this metal oxide sort of semiconductor technology that's used on it, along with it's like a glass substrate, a metal oxide stroke glass substrate that is heat conductive, and then it dissipates the heat on the edges to the heat sink. so it's not as involved as you might think, really. And then the attenuator sections are down the middle. Now, I found out what caused the problem. This is the socket, and this has there's two sockets, one male and female, but the female, when I tip it out, has the little gold pin, which is just here. Now that little gold pin has obviously got like a little plunger stopper at the end, if I can get it to turn round, so that sits inside that little hole there on the N-type female. So what I've done on this one here, I've got a gold pin which I have put inside this receptacle, and you can just see it there wobbling about inside this gold pin where my fingernail is, and I've cut it right low profile so that when we fasten it on, it should make contact then with the circuit board edges, which is obviously on the edge there, and it just bonds to that, because obviously you can't solder there, because if you did, the whole substrate would heat up and it could cause damage to it, or it will dissipate the heat away from the soldering iron, so it's a mechanical contact instead. So we'll reassemble it with that and see whether we get it working. Okay, it looks like we've repaired things. We've got the tracking generator connector back up again, going through the attenuator. If we look at the screen now, it's saying that it's 6 dBs across the frequency range of basically 1 kilohertz right up to 3 gigahertz, and that's the marker level. Now I'm gonna wiggle this, put stress on that. It's not changing it, so it's remaining constant, which is good. So that's a good result. Obviously we've now got the attenuator repaired now, you know, so that's an example of something that you could have in the workshop that you don't know is faulty, and then all of a sudden you want to use it for an experiment or something like that, and then you find out that there's a problem. I mean, you could clearly tell earlier in the video, if you look back again, we were in the noise floor, like neg 50 dB, something like that, with the attenuator level quite sensitive, and we couldn't, the RF attenuator, I mean, in the tracking gen. So, you know, we couldn't establish a 6 dB difference between the inputs and outputs, but now we can. So, you know, it just shows you that that's a typical example, really, of what can happen and how you can perform repairs on things, such as attenuators, for example. Not just filters and alignments and things, but, you know, in a fault diagnosis situation. Now, if you watch the video I did on the Roden Schwartz CMS54 radio test set, that had a broken attenuator, same kind of metal oxide glass substrate PCB in that than what was in this, really. Very similar design, but it had a fractured across it, and when you put physical pressure on it, then the performance on the track gen went from being all weird to bang straight across all the frequency range of the attenuator. So you could clearly see that there was a definite breakage in the connection. You see, as well, RF can jump gaps, particularly at high frequencies, so it can represent very little losses at high frequencies, but at low frequencies it would represent a massive loss. But when you get into microwave spectrum, for example, you only need to have an airline cracking something, and when you sweep it at particular frequencies across a wide dynamic range, a wide frequency band, then you can see that it has a weird unlinear, ununiform response. And then you know, so this is it. Signals can transform across gaps quite easily, especially at high frequency, UHF upwards. So that's a very typical example of a failure on an RF component that we've now repaired. And no matter what you do, it's fairly straight with a response. So we can put that back into service now, confident that when we connect something to that, that's going to have a 6 dB attenuation. So I'll get a filter on next and we'll have a look at a filter response. But as you can see, that RF attenuator can work right up to 3 GHz. So if I, for example, select the marker, we have the frequency here, and if I adjust the marker frequency by turning the rotary control knob here, and we adjust that right down in frequency, and you can see we're going right down there to basically 0 megahertz, right the way up, and it's remaining, the response is flat. Now if that attenuator couldn't work above a gigahertz, then you would start to see the curvature go off, and or it might go up in probably get more lossy as the frequencies go higher, but it wouldn't be uniform 6 dB. It would start to wave about or fall off quite sharply. Go weird. As you can see, even at 2.67 gigahertz, it's maintaining roughly 6 dB right up to 3 gigahertz. So I dare say if we swept it on the microwave test set right up to perhaps 20 gigahertz, it'd be interesting to see what response it gives and how much attenuation it gives right up to 20 gigahertz. But that's an example of that. So we'll get a filter on next. So just before we do the filter, I just want to demonstrate the principles of what happens when an RF connection is broken, as in instead of being connected, it's open like that. And so what we've done, we've got this connector loosely coupled, so it's not actually connecting at all to the inner pin in there, and the pin in this aren't touching. They've got an air gap in the middle of them. And so this is a sort of information that I was conveying earlier, in the fact that the trace was starting at very low frequency and going up to a very high frequency, 3 gigahertz, and you can see it's not at all very responsive at the low frequencies, because obviously as you get higher in frequency, then RF can transform across a gap, particularly at UHF frequencies and above, whereas at VHF and HF frequencies it doesn't transform very well across a gap, a short gap with only a small surface area anyway. So that's why you get that very sharp cut-off at the lower frequency ranges. And so just as an example, if I select the marker and then we move the marker now and have a look at the frequency, so around about a gigahertz there up to 3 gigahertz, it's just only slightly falling off, but it's more or less straight. And then below a gigahertz at 800 megahertz, 7, 6, 5, we're still in the UHF spectrum, 400 megs. And then when we start getting to the VHF spectrum now, then it really falls off really sharp, as you can see. So that will be a good idea. Obviously if you're sweeping up here, for example, so if we were to set the frequency of start frequency of say 2 gigahertz and the stop frequency, leave it at 3, it looks fairly flat. So if you're just looking at that area on a spectrum analyzer while you're doing fault diagnosis and repairs on an RF instrument or component which is not working correctly, then you can lead yourself down this path of thinking, well, it's actually got 20 dB attenuation, it should have 6, but it's flat. And you might be looking in other areas then thinking that it's not a broken RF transmission line, for example. It could be a defective component, and it leads you to believe that those losses are incurring because the sweep in this particular narrow frequency spectrum looks like it's fairly linear, so therefore you would think perhaps a transformer transistor's not amplifying properly, or a particular RF stage has got a defect in it. So you might start leading yourself off looking at other areas of the circuit, power supply, RF sections, gain of devices, supply lines to devices, inductive and capacitive components in the circuit, and start delving off into all sorts of different areas. Well, the actual real fault is staring you in the face, which is a broken track, a dry solder joint on the RF transmission line, or a crack, or an RF connector that's not quite making properly on the inner pin. Those kind of things are very, very easily missed, and this demonstrates it perfectly. At high frequencies it can transform across quite clearly, but obviously then at low frequencies, if we change the start frequency again to 1 kilohertz for example, you can see it really rapidly falls off. So that's a very good demonstration of how an open RF transmission line can look on a spectrum analyzer. Okay, so we're back again with the filter now. We're connected on the tracking generator. Got a track gen coming into the input and then the output going back to the spectrum analyzer input. We're quite lucky on this one because this filter does actually tell us what frequency it works on, 894.5 to 905 megahertz, and these are the tuning elements here that you can tune it with if you want to change its frequency characteristics. So this is a trace that we've got on now. I've just put these frequencies in, a start frequency of 800 megahertz and a stop frequency of 1 gigahertz. If we put the marker on, and I will move a marker now, which is on the far left of the trace, and we'll get that to go up. And you can do a bandwidth measurements at 3 dB points. So this has actually got quite a bit of loss actually at minus 12 dBm, considering we've got an input signal of a reference level of 0 dBm. Does seem a little bit strange, I must admit. So it seems quite lossy for some reason, does this filter. So it has actually got a bit of a loss. So that's the input and that's the output. So it does seem to be a little lossy. I wouldn't have expected it to be that lossy, to be fair. So I think what I'll do, I'll check the Rfgen levels to make sure that we are actually generating 0 dBm. Now it should tell us somewhere on the screen about that. So let's have a look, see if we can find it. So that's the frequency resolution bandwidth information, and the reference offset is 0 dBm. So it all looks okay, and yet we've got a minus 12 dBm signal, so it does seem strange. Let's have a look at the tracking generator again, and then we've got there, look, output level. So let's just have a look at that a bit further. See, minus 10 dBm. So that's trickiness, you see. That's, we're thinking that we were still on 0 dBm and we're not, so we need to change that minus 10. That's the level that's coming out of a tracking generator to the filter. So we've made a reference level of 0 dBm just here, so everything's in relation to 0, and we're actually generating a lower level of 10 dBs less coming out of here. So that's making the measurement appear that there's excessive loss in the filter. So again, you need to check your measurements carefully. So we'll enter 0 in there and then dBm here, and then as soon as I do that, then we are actually now on the top line, because 0 dBm is on the top line. If I pull that down with the attenuator by pressing amplitude and then the attenuator, bring it down there so we can see the top of it nicely, we've actually now got a 1.46 dBm loss, which is about right really for a filter. You'd only get a couple of dBs lost normally across a filter, 1 or 2 dBs, between 0.5 to 2 dBs at a push, depending how good a quality the filter is, and we have to factor in the RF cabling as well. So that's where you've got to be careful, you see, with your measurements, because if you weren't careful in checking the instrument and how it's set up, you could think there was a fault with that filter and then start taking it to bits, unsoldering it, you know, aligning it, prattling around, spend hours and hours and hours faffing around with it, only to find out that it wasn't that at all, it was your test set. So that's another example of checking again, because we did have that set to 0 dBm earlier, but since I've shot different parts of the video, I've made a cup of tea and I've switched the test set off while I went to make a cup of tea, and then when I've come back, it's defaulted back to the configuration settings within the instrument of -10 dBm for the TrackGen output. So you've got to check things, you know. Or you could go to another measurement, for example, and then come back to the TrackGen and find out it's put the default level in, and therefore it's tricked you. So this is where you've got to be a bit careful with things. So that's the filter anyway, but we have got additional measurements that we can make here. If we just have a look, we've got scale per division scale, internal amp. Oh yes, that's the internal amplifier. What does that do then? Let's have a look. Oh yes, that clears it up nicely, doesn't it? Yeah. And reference offset for if we're using again an external attenuator, we can set that dB level. So again, if we were using this RF attenuator there that we were repairing earlier, which is 6 dBs, we would enter 6 dBs there, and therefore whatever power we're feeding into that RF attenuator will be compensated for in the readout on here. So that's when you could read higher RF power levels than the instrument can take. And likewise, no matter what the RF attenuation is, you can enter it in there as well. I think under where are we now? Let's have a look. I think there were other things. Limits. Let's have a look. I think we had limits, trace, max view, select mode, bandwidth, auto. We also had, I think under sweep time, single continuous, couple, what's couple, detector normal, average video bandwidth type, FFT and sweep. I did see somewhere where, I can't remember if it was under mode, spectrum mode and phase noise, that was it. There's a phase noise. So let's see what it does on that. So 900, center frequency 900 megahertz. So what we got then? We've got carrier square search, carrier frequency. We've got any phase noise, so what does that say then? Trace reference, sweep. Not sure how to get that working, that bit, but got something down there. 10 megahertz reference, carrier search. We'll use carrier search then. Searching for carrier. Oh, it's probably because we're in the TrackGen mode. That'll be why. I hadn't realised we're in the TrackGen mode. So I think it only does a phase noise adjustment when you're actually feeding a signal in there that's from another source, but I'm not sure. I'll have to look in the manual for that. Right, well what we're doing now, we're doing a phase noise measurement of an incoming RF signal fed in on the RF input port. We've got here a signal generator set up at 1 gigahertz at 0 dBm, and so that's basically the phase noise that's coming from that signal generator. So as we can see there, we've got a green trace down the middle, which is a smooth part, and then we've got the trace measured, so that's the actual measure is in yellow, and the very fine green line that runs through the middle of the trace is the smoothed out version of it, and so that gives us the phase noise of what's coming out of that signal. So yeah, so quite interesting, and does do some processing. So part searching the carrier. So it just takes a moment while it hunts the carrier down and then processes the noise level on it. So that's the measurement you can do there, which is quite interesting. And again, flat value scale division, 10 dBs, and flat value. Measure log plot. A logarithmic plot of phase noise. So there's also, I think, an FMD modulator as well somewhere, which I'll have to preset it because it's not responding with the other buttons at the moment. So we'll just go to preset. One of the nice features about this as well, when you're injecting a signal in there and you don't quite know what frequency it's on or where it is, other than entering all the bits and bobs, that you can actually go to self-tune. Now if I do preset there, lights, stop responding, there we go. Right, if you just click tune there, press tune, and it'll find the frequency that's coming in and put it right in the centre of the screen. So that's quite a handy little feature to have as well. Now I do think I saw somewhere an FMD modulator. Let's just have a look. Zoom display on. Let's have a look at that. So that's another little feature. Full screen display line on or off. Threshold line, zoom center, zoom span. There's another thing there. Screen title, so you can title the screen. White mode, graticule mode, and grid text as well. So you can obviously label the measurements too, which is quite nice. So there's a fair bit that you can do. There's menus within menus within menus, you see on this. That's the thing. There we are, look. We've got the FM scale as well, an AM scale. So we've got D mod as well, AM D mod and FM D mod. So we can put D mod on. And when I then introduce modulation on here, if I can do mod, and then I think it's on off, 1.5 kilohertz or 1.2 kilohertz. I'll put 2 kilohertz in just for good luck. Let's have a look. FMD mod is off. Audio level, spectrum view is on. Audio level, audio sound is on. This is a new one. Let's see whether you get some squelch noise when you undo the signal one. There you do. So it's demodulating the audio. FM1 deviation. I'm not sure why it's not coming through. But you get the gist of it anyway. There's means of setting it up. I think the signal generator that I've got set up is not producing the mod. So it says it's off. Let's have a look. We'll see whether we can get it to FM2 is on 2 kHz. Mod frequency 1 kHz deviation. So unless it's because the level's too low and it needs say 20 kHz or something like that. But can't figure it out at the moment. I'll have to come back to it once I've worked it out. Okay, we're back. We've managed to figure it out. It was the signal generator that I was using to send a signal to this. The mod was disabled. That's one of the things about these Marconi IFR SIGGENs, which I'll go into when I do a demo on those. You can set the mod on to them, but then further on it's still set to disable, but it's hidden from you. It's just a very difficult instrument to drive as the other SIGGEN. But anyway, we're generating a signal now. We've got the mod frequency, which is 1 kHz, which is what I'm injecting in down there, and we can see there that the range is from 0 basically here to 20 kHz in frequency, and then we've actually got the audio sine wave that we're demodulating, and this gives us the frequency location of the tone. Now if I change the frequency, if I can work out how to do that, frequency on the there we are. Let's have a look. You can put square wave on. And then change that to 10 kHz. It's now injecting a 10 kHz tone, which you won't be able to hear on the microphone, but basically it's appearing there now in the middle of the screen. Let's put 5 kHz in, then 4 kHz, 3, 2, 1, 500 Hz. So then it's right down at the left. So that shows you what you can do with demodulating AM and FM on it too, which is quite useful. One of the measurements that you can do with filters such as this as well is do the 3 dB bandwidth measurements. That gives you the bandwidth of the response to the filter. So here we've set that measurement up, which I'll show you how to do that in a moment, but basically you can look at the 3 dB points and then it will tell you the total bandwidth of the filter, which is 14.4 megahertz in this case. But basically if I just knock that measure off there by pressing F1, so we've got that. As long as you've got your marker set up on that section of the signal trace, then it'll find it, because obviously if the marker's way off down here, it's trying to look for bandwidth of something that isn't measurable down here. So just bob the mark at the top of the peak, or you can do that using your markers, where you can select peak find or peak to center frequency, for example, and then it's under measure, and in measure then you've got occupied bandwidth that we looked at earlier, so it'll give you the occupied bandwidth. You can also look at channel power obviously as well. Then you can also look at adjacent channel power, and then you've got your 3 dB points. There's intermodulation and total power, which we looked at earlier, but basically this feature here then calculates the 3 dB points as well. So that's a nice little feature as well that you can go into. There are other measurements as well which I've not shown, but just to quickly go over those. If I select this measurement off, under mode, I think it is, then you've got spectrum mode and phase noise, We looked at both of those earlier, but what we didn't look at is the vector analyzer. So then we have obviously a vector analyzer. So we've got these, a spectrogram, we've got power versus time, I think, IO pulse vector, IO wave on time, and all sorts of mod analysis and various other things that you can do with it. So it's a very advanced spectrum analyzer. You know, it can really do quite a lot with this instrument through these different modes, and then go back to spectrum mode. Now, as well as that, you've got other features as well with the display. You can adjust the display, so you can, for example, go to zoom on a display as well. So you can really pull out the top of that waveform, and then you can alter the zoom in and out. You've also got threshold line as well. You can put that on if you want, and then adjust that. It came on as a green line at the bottom. Display line. So you can colour code your graticules, and then we've got white mode as well if we want, so we can invert the video for whatever application that's used for. Screen title, so you can add in, you know, fighter aircraft filter, something like that, you know, as a title if that's what you're doing. So there's quite a lot on there that you can do. Dual windows, that's quite a handy little feature as well. So obviously when you enable that, you know, you can make comparisons. Text position, grid text, so then you can add annotations or markers, and then we've got different screenshots, screen notes as well, or mute. Screen note 1 to 8, 1 to 9, so you can add all the different notes on the screens and then save them. Now under, I think it's system, I think you can set up things like your printer setup as well, so you can go into that. Then there's GPIB setup as well, TCP settings for Ethernet port, and then option info, so it'll tell you in there what option activates or display options. And I'm wondering if some of those options can be activated through software just by entering the right passwords in as well. And so there's quite a bit there, and so yeah, quite a bit to it. So that's how you can do measurements of a bandwidth. Now under frequency, I think you can put frequency counter mode in. I think under mode, you get different modes, you see. Spectrum mode, and then I think you can display, I think there's a button called display somewhere, I think, and you can then put up frequency counter mode as well, which I've seen. Let's have a look here. Sure, it's here somewhere. Marker, select marker. I'm sure it's in frequency counter mode. Probably gone past it and not realised it. See if we can find it. Frequency counter. There we are. So then you can select that, and then it will then give you the signal frequency of where the marker is. Obviously if you move the marker about by pressing the marker and then moving that, then the frequency will change as well. So if you've got a particular frequency you're locked on to, at least you can read the frequency as well. Yeah, so that's a little rundown. I think you get the general idea that, you know, it's a fully featured spectrum analyzer, very powerful, very capable instrument. You can do some very advanced measurements with it. I would say that it's a very worthy spectrum analyzer to own if you ever get a chance of owning one of these. And I think really the general overview of what we've done so far covers most, if not all, the functions of the tests of the spectrum analyzer, right the way from beginning to end of all the available features that's on it. But there's still more that I haven't been able to show, simply because the length of the video will be too long, and in some of the other measurements that are more complicated, more complex. So again, it's something that if somebody owns one of these, that a lot of it will be down to reading the manual and gaining the information from the manual of how to perform certain tests as well, because there's multiple layers of menus that you have to cross-link. So it's not just a case of going to one measurement. In order to set up that measurement, you need to enable other features as well and configurations elsewhere within the spectrum analyzer settings to set up that measurement. So then, you know, certain things become enabled in other menus when you've already gone into the base menu and activated a feature there, or that you're wanting to set something up in a particular way, then it will automatically enable other things that will become visible on the right hand side. So it's like a sequence of things that you have to abide by in order for you to get to later stages in the measurement. So there's all that sort of it as well, but very advanced, very powerful spectrum analyzer. This one goes up to 3 GHz, as I said at the beginning of the video, but you wouldn't be done by if you pick one of these up. And of course, the nice thing about it is I find the display very clear, very sharp, high contrast, very good to see in high light environments, ambient light environments such as bright sunlight environments, things like that. It's a pleasure really. It's very easy to use, and I'm very pleased with it. So we'll hand you on to the next part of the video. So this is where we've now selected spectrum view, and we've actually got the frequency deviation, the level that's coming in, which is 10 kHz, and then the actual frequency itself, the mod frequency too, which is again another little useful feature. And we've got window type, so again we've got information there that we can look at. FM scale, AM scale, window type, spectrum mode, audio level. That's where you can turn the volume up that of the demodulated audio, so you can turn that off, and then audio off as well, so you can then recover the sine wave from the demodulated signal. So quite interesting, amazing what you can do with it. It's quite featured, so I think we just about covered it all now really, what it can do. I'm sure there'll be more, but it was just a general video really, just to give you an idea. And we'll just press the tune button on there and then get it to tune. So we've got mod on it at the moment, so it's going to display modulation. So anyway, I hope you've enjoyed the video. I just didn't want it to make it too long, you know, but at least you've seen a repair in progress of an RF attenuator. So that's a typical example of using a spectrum analyzer, and a filter as well. I always like to show an instrument in use if I can, doing a particular thing, not just doing a measurement, you know, that's boring really, it's just doing a measurement on its own. But to actually fix something, repair something using the instrument, what kind of an application that you can use an instrument for, gives you that that idea, that improvisational aspect where you can use it for fault diagnosing amplifier stages, to signal tracing, to sweeping a filter or an attenuator and then localizing faults within that device to repair it, as I've shown you here with the RF attenuator problem, which was a genuine fault. I didn't know that existed because it's the first time I've ever tested that since I bought it. So yeah, it just shows you, doesn't it, what you can do with the instrument. Nice little spectrum analyzer. I think it will look very smart connected to the big screen monitor, and very useful to have in the workshop. So a nice little addition. So thank you for watching the video. If there's anything that you'd like me to sort of put in future videos, any particular types of tests or equipment alignment, radio stuff, anything like that, just put it in the comments. Please subscribe if you like the video. There'll be more of these videos coming, and thank you for watching, and see you again in the next one. Bye now.